All right, in this video we are going to talk about the proof of Theorem 1.3.1 in our book. The theorem says that if G is a connected graph with P vertices and Q edges, then P is less than or equal to Q plus 1. Again, the standard warning, if you are watching this from another class, then make sure the definitions that we are using in this class might be different, slightly than the ones that you are using. Okay, so just to illustrate the theorem, let's take a look at some graphs. P0. This is a connected graph, and it has 0 edges, right? So we have one vertex, right, and 0 edges. So 1 is less than or equal to 0 plus 1. 1 is less than or equal to 1. So certainly true for this graph. That's the only connected graph with 0, with no 0 vertices, right? And then P1, you can look at that. Here I have 2 vertices, 1 edge, right? So 2 is less than or equal to 1 plus 1. Here are, for P2, looks like this, right? And so on and so forth. So you can verify those. And so now we want to take a look at the proof of this theorem. So I've went ahead and written some things out. So what we're going to do is prove this by induction on the number of edges in the graph. All right, and so the base case, right, would be P0. That is the only connected graph, right, with 0 vertices, would be P0. And P is 1, Q is 0, so 1's less than or equal to 0 plus 1. All right, and so that would be the base case. And the induction hypothesis, right, that is the thing that we get to assume is true, is that if G is connected with P vertices and N are fewer edges, then P is less than or equal to N plus 1. Okay. And then what we have to show is that if G is connected with P vertices and N plus 1 edges, then P is less than or equal to N plus 1, which would wind up to be N plus 2. Okay? So that's what we have to show. So going in that direction, let G be a connected graph. With P vertices and N plus 1 edges. All right. So what we are going to do, again, right, in proof by induction, we want to somehow be able to use this induction hypothesis here, right? So so the first case that we're going to look at is if G contains a cycle. So if G contains a cycle, then G minus E is connected. Right? Remember we proved that lemma in a previous video? Okay. G minus E has P vertices, right? Because it has exactly the same amount of vertices as G does, right? And it has N edges because we deleted one of the edges, right, out of out of G. And so that means that it applies, the induction hypothesis implies, right? So by the induction hypothesis says that P is less than or equal to the number of vertices of G minus E is less than or equal to the number of edges, right, plus 1. All right, so p would be less than or equal to n plus 1. And, right, n plus 2 is always going to be bigger than n plus 1, right? So 100% we have that p is less than or equal to n plus 2. Okay. All right, so if G has a cycle, then we are good on that. All right, so next up, what about if G does not contain a cycle? So G minus A has P minus 1 vertices. And let's see, G had P vertices, right? So G minus A has P minus 1 vertices. We deleted one, right? And then G minus A will have N edges. Because G had N plus 1, we deleted one. All right, so the key thing here, right, is that G minus A has N or fewer edges, right? And so the induction hypothesis implies that the number of vertices of G minus A is less than or equal to the number of edges plus 1. Okay? Because, right, we know we are allowed to assume the induction hypothesis is true, right? And that is, if the graph has less than or equal to n edges, right, then the number of vertices is less than or equal to the number of edges plus 1. And so we have that G minus A has n edges, so this is true. And then just a little bit of algebra, right, we get that P is less than or equal to n plus 2, right? So we've shown that P is less than or equal to n plus 2, and that's exactly what we have wanted to show about G, right? And the number of vertices is less than or equal to n plus 1, which is 2. So by the principle of induction, right, that actually the strong form, right, with the less than or equal to, then actually you might be able to get away without that, but regardless, that's by the principle of mathematical induction, right? We've shown that the theorem is true, right, for all non-negative integers. Okay. All right, and so that is it for this one.